Thank you.
This is the TIMS system unit. In the top, we have, in these units, we have 12 slots for the plug-in modules that we were just talking about. In the bottom are all what we call the fixed modules, the modules we use most commonly. Things such as DC signals or buffer amplifiers, or most importantly, our master signals. And let me show you the master signals. The first thing with the master signals is the blue waveform is what we call our fundamental message. It's a 2 kilohertz sine wave. Of course, we have audio oscillators, we have other signal sources, but this 2 kilohertz is synchronized to the other waveforms, including the red one, which is our passband signal. Our passband signal is 100 kilohertz. So all our modulation, AM, FM, MSK, OFDM, ultra-wideband, spread spectrum, frequency hop spread spectrum, all those analog and digital modulation schemes are all set at 100 kilohertz. And here you can see why. Because we want the student to see that passband signal. If we chose 1 megahertz or 100 megahertz or 1 gigahertz, the student would just see a block, wouldn't see anything. Is this valid? Yes, because TIMS is a modeling system. From the equations before, you saw omega C. Omega is 2 pi f. If f is 10 to the power of 5, 100 kilohertz, or 10 to the power of 10, the mathematics is the same. It's just scale. It doesn't matter. The fact that we're not using RF, real RF gigahertz frequencies to create these modulation schemes, theoretically, is of no consequence. So, using simple patching leads, using simple instrumentation, the student can create all of these analog and digital modulation schemes and actually see what those modulated signals, what those passband signals look like on a standard oscilloscope and standard spectrum analyzer. So, here with the inbuilt instrumentation, this is the TIMS 301C with the 2-channel inbuilt instrument. The 304C has a 4-channel PC instrument. But here you can see the blue is the 2 kilohertz message and the red is the 100 kilohertz. And most importantly, as I mentioned briefly, this 2 kilohertz message, the 8 kilohertz sampling signal, and the 100 kilohertz signals are all synchronized. And what that means is, this means synchronized in a telecommunications sense, not in a digital electronic sense. In telecommunications, synchronized means that the phase relationship between the signals is constant. If the phase relationship wasn't constant between these two signals, one would be triggered and the other one would be running. So we have these synchronized signals so that students see if it's AM or if it's FM or if it's a sample signal, sampled and reconstruction signal. What they see is, in the first instance, just basic textbook images. What you see in a textbook for an AM waveform is what the student will see on the oscilloscope, either the virtual scope or the real scope. So in the first instance, the students see what they see in textbooks. Then you can develop it further and put in an alternative message, which is not synchronized, and now the student will actually experience what synchronization actually means in telecommunications. So let me jump ahead and show you. So I'm taking the adder, which has 2 inputs, 1 output, and 2 control knobs. So any module can go in any slot, and it's all hot swappable. So I can plug it in and pull it out in real time. So let me connect this 2 kilohertz message to 1 input, and I'll connect this variable DC, you see, down here, to the second input. So the output is 2 kilohertz sine plus DC. So you can see as I turn this knob, so there is an example of an adder being used. If I disconnect the DC, all I have is gain control of that message. And notice something else. We do this on purpose in different modules. Notice that the adder is inverting. So why do we do this? Because in telecommunications, when signals are transmitted down a coax cable or through the air, how do you know, how does the engineer know what the original phase is? Phase inversion is very common. So we introduce some of these concepts, like inversion, like different, for example, the multiplier I'll show you, different gains, different gain coefficients, because we want the student to actually look and think and measure and understand what's happening. So this is not just simple spoon feeding. This is the student thinking about, what does phase inversion mean? Is it an issue? In some modulation schemes, it doesn't matter. In others, it does. So it introduces these concepts to the students. So let me, for simplicity, take out the adder and I'll plug in this multiplier. You see the multiplier has 2 inputs and 1 output. And here this switch is coupling, where the inputs are either AC coupled or DC coupled. So I'll plug this in. So what I'll connect 2 kilohertz to 1 input. I'll connect 100 kilohertz to the other input. So I'm now multiplying 100 kilohertz with 2 kilohertz. And if I look, there's the correct trigonometric result for 2 kilohertz sine multiplied with 100 kilohertz sine. So in communications, this is not so much trigonometry, but referred to as double sideband suppressed carrier. Now, with the virtual instruments we include, we allow students to look at this important idea in telecommunications of the student constantly thinking time, frequency, time, frequency. So here we can switch, and here we can see the blue is the 2 kilohertz message. Here is the lower sideband, 100 minus 2, and here is the upper sideband, 100 plus 2. So notice when I have DC coupling, there's obviously a small DC offset that's coming through. And look, you can see here, see this suppressed carrier that's what? It's about 30, 35 dB down. That's because the small DC offsets are feeding through. If I AC couple and block the DC offsets, look what happens to that carrier. It's now 55 dB down. So you see, TIMS is not meant as an ideal system. These are real signals with DC offsets, bandwidth constraints, phase constraints, so the student can look and learn what are they actually looking at? What's the difference between DC coupling and AC coupling? And you can ask the student, measure these signals and have a look. Why is that happening? What's the DC? How much DC is there? And there's probably 3 or 4 millivolts of DC coming through. That's it. So this gives you an idea of using the TIMS modules. You can see how they use inputs and outputs and looking at waveforms, and looking at the instrumentation, the oscilloscope, and the measurements and the time and the frequency. So this covers a number of the concepts that I've included in session 1. Let's finish this session by using 2 modules to build an experiment. So let me disconnect everything. So I will now, again, take the adder, remembering that any module can be in any position in the rack, and they're all hot swappable. So for this adder, what I'll do is I'll take this 2 kilohertz message you see, and I'll put it to one input of the adder. The other adder input, I'll take variable DC, and I'll patch that into the second input. So here we can see the output of the adder is 2 kilohertz plus DC. I will now patch 2 kilohertz plus DC into the input of the multiplier. That's there. And now I'll patch 100 kilohertz into the other input of the multiplier. So we have 2 kilohertz message plus DC multiplied with 100 kilohertz gives us, well, an overmodulated AM. Why? Because I'm a bad student. I didn't adjust. I didn't measure the parameters to get the desired result. And notice that this, what you can see here and even on this scope, are real textbook-like images. So let's look at the spectrum. So here we can see the blue is the 2 kilohertz message. Then we have the lower sideband, 100 minus 2, the carrier, and the upper sideband. Now, let me just skip across and say, let's say the student sees this. So here's an AM signal that's being clipped. So in the time domain, this looks nice, it's flat, it's good. But why is clipping bad? Why in the mobile phone network, why do the base stations, why do the signals have to be adjusted to make sure there isn't clipping? Well, let's look at the spectrum. Aha, you see, what does clipping produce? Clipping produces a lot of harmonics and a lot of noise. So here is a very simple demonstration, even using old-fashioned AM, to show why is clipping bad. So if we go back to this point and I adjust, here you can see now we're generating. Now from the spectrum it looks a clean AM waveform, and there it is. So this shows you how with the TIMS experiment, you as the professor, as the lecturer, you can decide what additional concepts you want the students to be exposed to. So you don't have to just follow our lab manuals, of which we have some 5,000 pages of lab manuals. You can take our experiments and say, well, this is good, but I want to edit it and I want to add other aspects that are important in my program. That's why, as I said before, you can choose the experiments that match your curriculum, you can choose how deeply you want to go, and you can choose what variations, how you want to customize those experiments to suit your students and to suit your curriculum. Next, let's look quickly at, very quickly, at a very interesting idea of recovery. So let me adjust this so it's reasonable. So I'm passing the AM signal through a precision rectifier. If I now pass this AM signal instead through a diode and through an RC low-pass filter, look what we see. We get the recovered message, but you see the ripple in the recovered signal? Is this a mistake? Is this an error? Let's look at the spectrum, and we'll see. So there's the 2 kilohertz message, and we can see, because we're using an RC filter, you can see from the roll-off that it's passing some 100 kilohertz components. So it makes sense. So now we're introducing the concept of an RC filter compared to a 5th order filter. Let's use a 5th order filter instead. And I'll just quickly patch this across. And look. So why don't we see 100 kilohertz ripple? Because look, at 100 kilohertz, the roll-off of this filter has completely suppressed the 100 kilohertz component. So here is a simple demonstration of showing the student very quickly and very easily, what does it mean to have a first order filter, a simple RC, compared to a 5th order filter. So this is an RC, the filter. So when the students have been calculating those roll-offs, now they can actually see in the time and the frequency domain what this means. Okay, do you have any questions on this practical side that I've just been talking about? No?
Yeah, just a comment is it's very good because you can see the students they can do, because basically what I'm doing now at this stage, I am using MATLAB and simulating the students to see this one. So having the teams, they can see the simulation. I think what in Melbourne doing, they're doing the simulation and also showing the students to building up and to compare those two, and they can see they had the simulation in MATLAB. And they're doing actually they use LabVIEW, but we're using MATLAB now, and they're using the teams, and they can compare and can see it. Basically, they can build it by themselves, the students, and they can see in the oscilloscope the same waveform what they do in the simulation. So I think doing this experiments, the students, they can see, feel, and they can see all these experiments. So that's pretty good. Thank you.
Look, your point is really valid. It's really important, because if you do now experiments like, for example, QAM or some phase where phases are involved, and the students do a simulation of that, the results they'll get will be mathematically perfect. But when they implement them on TIMS, they'll actually see real live signals, and they'll see that the signals using real electronics are not 100% mathematically perfect. There are little offsets. So you'll see other quadrature components and so on, and I can demonstrate that. So that the signal will never be 100% null. There will always be a small component because of the nonlinearities, because of the phase and frequency effects of real electronics. And another example is I'll just break this up and give a really good example that was given to me by two professors, one in Germany and one in America. they gave the students a tutorial question, so they must have been using the same sort of textbook, to design a front-end filter for a receiver. So they gave the students the signal, all the parameters of the transmitted signal and the channel. And one student came up and said, oh, look, I use MATLAB. I really, I understand it. And here's the optimum filter for the receiver. The professor says, and again, this happened twice. And the professors asked, oh, what's your result? And the student says, the optimum filter is a order 256 filter because look at the great effect. And the professor said, oh, okay, you've understood the question, but so I'll give you 49% for your work so far. Now go to the lab and build me this filter, and I'll give you the rest of your marks. Because the simulation can go off and give perfect mathematical results, which are not always realizable. So doing what you're saying, allowing the student to do the simulations and then to look at real signals is actually an added value. The student is learning a whole lot more about simulation and the real world. And this is what engineering is all about, isn't it?
Yes. Thank you. So I don't want to get ahead. Do you have any experiment or showing us for digital communication?
Yeah, if you look at the page 7 of our brochure, you can see here as I go down the digital communications. I will show you one. I'll cover some of this, and then I'll do one very interesting spread spectrum experiment for you. But yes, if you look at page 7, it really depends what.
Yeah, Q and yeah. So basically, what I'm doing, also what we are doing, so the same like in Melbourne, we're doing QAM and PAM, and we are comparing. We're giving the students and to compare. They are doing a very big, they're doing one experiment, digital communication. This is in my course is Introduction to Communication Engineering.
Mm-hmm.
So the third experiment, it said the first one is like signal and spectra, just have a feeling they're looking for the different type of signals, but the spectra, the second experiment, they're doing AM and FM, and the third one is a big experiment. They're using the digital communication, and they're using constellation diagrams. Mm-hmm. And we're giving them to compare and to see what is the difference with the PAM and QAM. And we're trying to do different levels. Yes, so that is also, that's a big experiment. There's students for 4 weeks, and that's also important to learn the students about, because we have optical fiber communication. We're not giving any experiments, but we're doing for AM, amplitude modulation, analog and the digital communication. Mm-hmm. So you have the amplitude modulation, and we have the digital communication, one experiment. Yeah, thank you.
Well, in that list, it's up. The choice is quite enormous. From simple digital modulation, ASK, FSK, BPSK, through to QAM, QPSK, through to multi-level, 4816 QAM, 4816 PSK, and then constant amplitude schemes like MSK, Pyron 4D QPSK, and so on. So yeah, there's a huge selection of digital modulation schemes, which again you can choose based on what modules you originally have, or what additional areas you want to explore. So I will cover some of this, including the fiber optics, just in the next couple of minutes. So at this point, before I start looking at some of the individual modules and experiments, I just want to give you a quick overview of the manuals just in the next minute or two. So user manuals, like this basic user manual. I want to show you, I assume, let me just zoom in a little more. So the advanced modules and these basic modules user manuals all follow this principle. So if you open any of our user manuals, such as this one here, or what I'm showing in the screen, the user manuals, there's the title, the name of the module. There's always a short description of what this thing does. There's a description of the front panel labels, then a block diagram for that, and then there's use, how the module is used, and basic specifications. So in this example, I've shown you essentially what every TIMS user manual looks like. It all follows this pattern. Next, we have 3 different kinds of experiments. So just let me quickly demonstrate these. First, we call the lab sheet experiments. These are single sheet experiments. They are, in some universities, they're used by students, and the professor just says, here's the essence of an experiment. Now develop the experiment to do it. Or most often, the lab sheet experiments are used by professors when they get TIMS to see, I'm interested in QAM. How do I do QAM? Or how do I do BPSK? Or how do I do a simple spread spectrum? So instead of working through a 10 or 20 page experiment, we have in 2 sheets. For example, sampling. Here, this is sampling experiment. What modules are used? What are the block diagrams? What are the basic principles? And what's the patching diagram? So these are lab sheet experiments. So you can see there's about 160 of these experiments. They all follow this one sheet that gets you into the experiment instantly. So lab sheet experiments are very good for you to quickly see, how do I implement experiment? So it saves you time trying to work out. Next, we have what we call student text experiments. So these are the more detailed experiments. These are typically, can be anything from 10 to 50 page labs. Obviously the 50 page ones are quite complex spread spectrum and experiments. So with these, if I come down to the start of the lab, let me go quickly. Okay, so here's amplitude modulation. Let me zoom in a bit. So here you can see the sections on the amplitude modulation experiment. So then we cover the modules that are used, some preparation.
Sorry. Can you please go back? I saw you have some tutorial questions. So what are those tutorial questions?
These. So if I go back to the previous experiment.
Yeah, tutorial questions. So what are those tutorial questions? That is, okay.
They're examples of explorative, just to further probe the student, for the student after they've completed the lab to see if they can answer these questions, if they understood what they just did.
I see. Okay, that's good. Thank you.
So first with the lab sheet, the single sheet experiments. Then we have some, honestly, I've lost count. It's some 12 volumes of these detailed experiments. And they are all available to you. The experiments are listed in a separate document where you can go through and see all the different experiments of the many volumes that are in essence summarized in that transmission model. So last, let me go back to another type of experiment we call explorative experiments, where there isn't as much guidance given to the student. There's the core guidance on the block diagram and setting up the experiment, but then in these experiments, they're open a lot more for the student to explore and to investigate different aspects of these experiments, and lots of opportunity for the student to record their findings. And so there are student versions of these experiments, and then there are the professor versions, which are 2 or 3 times longer, which have all the sample waveforms and all the results. So these are the 3 different kinds of experiments that we cover. And the reason I wanted to introduce these is now I'm going to go into this second session, because we're 1 hour into the presentation, where I'm going to start covering some of these individual topics. So let me switch to, let me just go back very quickly to this presentation and just finish some slides. So I showed you using an adder and multiplier using AM. We looked at the time and the frequency domains. We looked at filter effects. We looked at distortion and overmodulation. So what I've shown you up till now, I wanted to get to this slide to show you that with TIMS, it's not just these, modulation, demodulation, it's everything in between, where we have the transmitter, you see a noisy channel, so we model it so we can control the amount of noise, we can control the channel bandwidth. And then we have the receiver, and then we have instrumentation such as bit error rate. But if I go back to the noisy channel, it's at that point that the student measures and calculates the signal to noise ratios. So we don't have an SNR instrument. We have a true RMS voltmeter, or the virtual instrument, which measures true RMS voltage. So the student actually measures the noise coming through the channel, the noise voltage. They measure the signal voltage. And from that, they do the 20 log calculation to see where does this dB number come from. So they can see the eye diagrams, they can see when they're adding noise, so they can relate what this dB thing means. So if a student comes up and says, oh, I think I measured 100 dB signal to noise, a student who's actually experienced this will look and go, I don't think so. That doesn't make sense. So it gives students that feeling for where the dB comes from, because they're actually involved in doing it. And similarly for bit error rate, we don't have a BR instrument. We use an exclusive OR gate, as you can see in that diagram, where we compare the received data with a local version of that data, and they are synchronized up using the sliding window correlator. It works very quickly and very simply, so that the student can now plot waterfall curves. So in the same way that they can plot waterfall curves in a MATLAB simulation, they can now do that same QAM or MSK experiment and plot the waterfall curves, and now they can compare the MATLAB results or the Simulink results with the real electronic signals. And what they'll see is that the curves follow, but there are differences. And now they can think, why is there a difference between the real signal and the simulated signal? So this sort of finishes up this first section of TIMS and the TIMS experiment capabilities. So now, if there are no further questions, I will jump to my